Something like this. So you imagine, you go back in time to the emergence of the development of nervous systems. So there's cells that creatures use to produce motor output, and there's cells that creatures use to map the patterns around them onto themselves, and so that's the sensory layer, so to speak. Imagine sensory layer, nervous layer, motor layer. In simpler animals, you just have sensory motor cells. Then they diversify: sensory layer, nervous layer, motor layer. In fact, that's actually what you consist of when you're first developing in utero. After the blastocyte stage, when your cells differentiate, that's the differentiation: sensory layer, nervous layer, motor layer. So then you think there's a sensory layer. Now what's that sensory layer doing? Think about the world as consisting of patterns of all sorts. Like maybe there's an animal in the ocean and it's being subjected to wave motion. And so its sensory systems map the wave motion onto the motor output. So if you look at a sponge, for example, sponges are good examples because they're sort of half unicellular animals and half multicellular animals. You can take a sponge and run it through a colander and separate it out into cells, say in salt water, and it'll assemble itself back into a sponge. So it's sort of at the, yeah, amazing, eh? It's kind of what you do in utero. The cells somehow know enough to communicate with one another to organize themselves into an organism. It's unbelievable. We have no idea how people do that, because when you're in the initial form, blastocyte form, all those cells are identical genetically. And then all of a sudden they differentiate and they move to the places they're supposed to go. We have no idea how the hell can that happen? These cells are all identical, except for their position. So they're obviously communicating with one another in some unbelievably complicated way and saying, well, you're this sort of cell, and so you're going to differentiate that way. God only knows. But anyway, sponges can do this. Now, a sponge isn't complicated enough to have the sensory layer and the nervous layer and the motor layer. It's just sensory motor cells, if I remember correctly. But what the sponge is trying to figure out is it wants to get water through its pores inside, because that's how it eats. And so there's wave motion constantly, and so what's happening is the wave motion is a pattern, and the sponge is reacting to that in a patterned way. And it's really useful to think about what you're responding to as patterns instead of objects, because we think we react to objects, but objects are actually a specific subcategory of pattern. And so, because it also helps to explain perception. It's like, what does it mean for you to see something? Well, it means a bunch of things, but one of the things it means is, when I look at that thing, it manifests itself to me as a grippable object. I mean, that's built into the way I see it. So if you think about the way that you see that on the surface there, you can tell that it's separate from the surface because it has a bit of a shadow, and it's a different color, and it's obviously shaped for a hand, and so that thing tells you when you look at it that it's a grabbable object. Well, it's hand-shaped, like a stone tool would be. And so, the things around you in the world manifest themselves as patterns of utility. That's the appropriate way to think about it. You say, well, what does this thing mean? Because that's a hard question. Well, one of the things that your eyes do is, like, imagine you've got this representational surface at the back of your retina. It's made out of pixels, roughly speaking, right? Those are the cells. And what it does is map that pattern onto your retinal pattern. And then the retinal pattern propagates itself as a nervous pattern along your optic nerve, and then that manifests itself as a neurological pattern. And that neurological pattern manifests itself as an action pattern. And so the meaning of the object is the action pattern that is mapped onto the percept. And so what does this mean? This is what it means. You think this is a Piagetian observation. It's like one or many. One, right? Because I'm acting like it's one. But if I do this, then it's many. Why? One, two, right? They're separably manipulable entities. And so the concept of number is, in fact, predicated, at least in part, on the idea of singular usability. But you're mapping it. It's like, well, what is this? It's a key. Well, what does that mean? Well, I'm mapping that shape into this motion for that action. You say, well, it's not just a key. It's a weapon, right? And so that's because I've mapped it onto a different output pattern. But if you think about perception as the matching of patterns onto patterns, it makes way more sense. You can really start thinking about how perception works, because then you can also start thinking about unconscious perception. So, you know, the blind sight experiments show, for example, that if you've had cortical damage, so you think you're blind, you can't see objects anymore, but I show you a picture of a frightened face, you'll show a skin conductance response to it, and you think, well, how the hell can that happen? It's like I have to see the face in order to infer the emotion in order to have the reaction. It's like, no, you don't. You don't need that at all. You need a pattern recognition system that maps that right onto an amygdalic output that produces physiological readiness. You don't need the perceptible entity, because, you know, you think, you see something, and then you think about the thing, and then you evaluate the thing, and then you act. It's like, you do that, but there are parts of you that don't do that at all. Way faster parts, more primordial parts. And so another example would be Darwin's trick with the snake that I told you about. He'd go to this museum that had a cobra in a glass cage. And the cobra, he'd put his face up to the glass cage, and the cobra would strike at him. And he'd go like this. And there was no way he could control that. Well, it's because the part of him that saw the snake wasn't the part that was doing this. There's a part of him that does this to snakes. That's what it does, and it's way faster than you figure to see the snake, you have to, the image is obviously the image. The pattern is portrayed on the retina, it propagates backwards. To see it, it has to be elaborated up through a very complex set of neurological connections. That takes time. And so you're dead. Well, the thing that snake means this, that's like 3 neurons, super fast. And so what is a snake at that level of representation? It's like a snake is that which makes you do this. And then you could also say that at that level of representation, everything that makes you do this is the same thing, right? Because the same would be defined by the pattern that you manifest in response to that entity. So then your nervous system is layered, that's sensory layer, neurological layer, motor layer. As you become more complex, the sensory layer differentiates into the different sensory systems, and the neurological level multiplies in terms of its potential number of connections. So what happens is that you can map patterns that manifest themselves in multiply different ways to multiple motor outputs. So you start with a fixed action pattern, which is just like the sponge reflex. What's the world to a sponge? The world is what makes you go like this or like that. That's it. That's the whole world. The sponge has compressed the entire world into pores open, pores closed. That's it. 2 states. And then, well, once the nervous system gets differentiated and the senses get differentiated, so there's specialized kinds of cells, then you can detect more forms of patterns. You can produce more patterned output to that. But even more interestingly, and this is where the nervous system starts to come into play, the mapping of the pattern onto the output is no longer one-to-one. You can use the same pattern, roughly speaking, to produce all sorts of different outputs that are context dependent, because you might say, well, so, okay, I picked that up. You say, well, he picked that up. It's okay, well, what about that? You think, well, he picked it up. Well, yeah, I did, except the pattern of musculature that I used to do this is by no means identical to the pattern of musculature that I used to do that, right? I mean, the fact that the orientation is different is actually extraordinarily important. So well, my point is that with sufficient nervous complexity, you can take the same thing, so to speak, and map it all sorts of different ways, and human beings are unbelievably good at that. Okay, so now go back to when things were simple. So there's single-celled organisms, we'll say, and then they start to differentiate to some degree, and they start to propagate, and so then the environment starts to shift, because the fact of the prevalence of all of these competitors means the environment isn't exactly the same as it was when that system first evolved. New problems emerge. And so then there's selection pressure on those creatures to diversify to some degree. And then the diversification produces a transformation in the environment, and then there's pressure on those new entities to diversify some more. And so you get this weird bootstrapping process. maybe the environment is one thing when there's 10 of you, but a completely different thing when there's 1,000 of you. Right, so just sheer multiplication is going to transform the environment. And so then because the environment has now become more complex than it was, there's selection pressure to produce diversification in the underlying organisms. And that took a long time to get off the ground. Like, there were single-celled organisms for a huge span of history. I mean, if you look at evolutionary history, the amount of time that there were single-celled organisms is far longer than the time that there's been since there were multi-celled organisms. It's like Moore's law, you know, the law that governs the increase in computational power. You can trace that back to about the year 1400, something like that. So it's been going on for a very long time. And maybe you could make the same case from an evolutionary perspective. It's like the flat part of the curve is really long, but once it starts to move up, it starts to move up really fast. And obviously that's the position that we're in now. So single-celled organisms for a long time. Then they started to diversify. And then you could imagine, well, from the single-celled organism you start getting multicellular organism, and then it ends up with this tripartite structure: sensory layer, nervous layer, motor layer. And then that starts to differentiate, and every time there's a differentiation, that's conserved. And that's these systems, the motivational systems. They emerged a long, long time ago as emergent solutions to emergent problems, and you've conserved all of them. I mean, you've conserved your snake reflex, which is like 3 neurons long. So that's really, really primordial. But you've conserved function at almost every temporal level. So there's parts of you that are quick and dirty, and parts of you that are slow and sophisticated. And a lot of the contents of consciousness is slow and sophisticated. So it can't help you out in an emergency. But it can do, what consciousness seems to do is take your structure, it analyzes the worlds for, let's say, mismatches between what you want and what's happening. And then it either helps you alter the world so those mismatches go away, or it turns inward and modifies the structures that you're using. So if you're playing the piano, you've got this automatized routine. It has very little to do with consciousness if you've practiced enough, and you make a mistake. You stop, and you note the mistake, and you stop, and then you slow it down, and then you practice the new thing, and then you speed it up, then you speed it up, then you speed it up. And as you're doing that, the neural representation shrinks until you've developed this little specialized machine, and then you run that a few times, and now you can ignore it. You can look at the notes and just play, and away you go. And that's kind of what consciousness is doing all the time. You're laying out an automatized routine, and then if that doesn't produce the intended outcome, you stop, you become conscious, really, because there's nothing like an error to make you conscious. Then you do a high-resolution analysis of the space in which the error emerged. You rematch your motor output, your perceptions and all of that to make that error go away, and away you go. And so your consciousness is your consciousness seems to be continually building your unconscious, your procedural unconscious. And so to some degree the purpose of consciousness is to make you functional unconsciously, right? Because that's way better. You don't want to be conscious of most things, because it's just, what are you going to do? Be conscious of your digestive processes? It's like, no. If you're good at something, you hardly have to be conscious of it at all. So consciousness is something like an error detection and rectification system, something like that.